In this video, we're going to look at one method of finding the volume of a solid of revolution. And that method today is the disk method. Now, what is a solid of revolution? Well, it's fairly simple. Solid revolution is simply a solid obtained by rotating a region in the plane about an axis. So, for example, take a look at this region here. And imagine, if you will, spinning it about the y-axis. Well, the type of shape we're going to get would be a cone. Another common solid of revolution and so again, consider this region. And now imagine spinning it about the x-axis. Well then, in this case, that's terrible looking. That's better. Whatever. Let's draw it this way. That's even worse. There we go. That looks pretty good. Right? Is a sphere. And so these are examples of solids of revolutions. So let's suppose that f of x is greater than or equal to 0 over some interval a to b. I don't know, so look at something like this. And we're looking at that region. Right, now furthermore, let's suppose that we're going to rotate it about the x-axis. So then the solid we get I should call that f of x, right? Right, so if we look at this region, right, we rotate it about the x-axis, it has a special feature. All the vertical cross sections are circles. Right, so try to sketch this out. And it's going to look something like this. And we can have a cross section, let's say, right here. Right, so we'll take this as our cross section. At some point x. Now notice cross section at the point x is a circle with radius, call it capital R, equals f of x. All right, to find the radius, right, you just go from the point to any point on the circle, so right up there, right, and that is definitely f of x. So the area of this cross section, right, pi r squared, so pi times f of x squared. Right, well, we saw previously that the volume of this would be the integral of the cross-sectional area. Right? So it'd be the integral from a to b of pi times f of x squared dx. This is the disk method. So let's just write it more formally. If f is continuous and f of x is greater than or equal to 0 on AB, then the solid obtained by rotating the region under the graph and the x-axis about the x-axis has volume v equals pi times the integral from a to b f of x squared dx. By the way, the axis which you rotate is known as the axis of revolution. Right, so let's go ahead, calculate volume of the solid obtained by rotating the region under y equals x squared about the x-axis over 0 to 2. Okay, well, first let's try and get a visual. Okay. So Wolfram Alpha, extremely useful for this. Region under y equals x squared over 0 to 2. All right, now it's doing this weird stuff again. Let's copy that. Bring it over here. Let's try and make it a little bit larger. That should suffice. Y. Uh-oh. Sorry about that. My system seemed to have crashed for a little bit. Okay, here we go. So what I'm going to do is I'm going to draw the rotation in red. So we're rotating about the x-axis like so. And it might be difficult to see, right? But there is a slightly shaded region here. Right. Well, we already know what our radius is, right? F of x, which is x squared. So the volume would be pi times the integral from 0 to 2 of the radius squared, so x squared squared dx. So what we're really doing is we're doing pi times the integral from 0 to 2 of x to the 4th dx. Right, so pi over 5, x to the 5th, evaluate that, x equals 0 to 2, and we wind up with 32 pi divided by 5. Well, now let's consider a different kind of region. All right, so let's consider this region. Right, a region between f of x and g of x. And imagine what happens now if we rotate this about the x-axis. Right, well, let's try and visualize it. So what's going to happen? Right, notice what we have. It looks something like this. It's like a region within a region, right? A solid within a solid. Well, if we take a look at the cross section, right? Really, what we have is the cross section of the outer, which is still circular, right? And then we have a cross section of the inner. And what it forms is what's known as a washer. Right? So if I try to draw it off to the side here, this is the result. Right? We have an inner radius, which is in red, and we have an outer radius, which is in orange. And this is really a fancy way of doing essentially volume of the outer minus volume of the inner. Right? So let's just now write this out. I have no idea why that popped up. Excuse me. There we go. So what we're now going to do is now consider the region between the curves. Y equals f of x and y equals g of x, where f of x is greater than or equal to g of x, greater than or equal to 0 over the interval a to b. All right. So when this region is rotated about the x-axis, the resulting solid has vertical cross sections. I'm sorry, I'm going to say has a washer as the vertical cross section. The outer radius is f of x, and the inner radius is g of x. Okay? The washer has area. If we go up and look, right? Wouldn't it be the orange minus the red, right? It's the radius of the outer disk. I'm sorry, the area of the outer disk minus the area of the inner disk. So we're going to say A equals pi r outer squared minus pi r inner squared. All right, so factor out of pi. R outer squared is f of x. The inner radius, g of x. Therefore, the solid has volume v equals pi times the integral from a to b f of x squared minus one too many parentheses there. Right, pi times the integral a to b of the quantity f of x squared minus g of x squared dx. This is known as the washer method. Since it's really just a derivative of the disk method, I'm not going to write out its own formal theorem, right? But just be aware that this is the washer method. So what we're going to do is find the volume of the solid formed by rotating the region let's say between y equals x and y equals 1 over x over the interval 1 to 4 about the x-axis. Right, so again, typically speaking, pictures help. So we're looking for the region between y equals x and y equals 1 over x over the interval 1 to 4. Right, so there's our region, right? And we're rotating it. Right there. Well, in this case, we can easily see that our outer radius is x. Our inner radius is 1 over x. So volume be pi times the integral from 1 to 4 of x squared minus 1 over x squared dx. go ahead and evaluate this, right? We're going to have 64 over 3. There should be a pi on the outside, right? Plus a quarter, minus a third, minus 1. And what we should wind up with after everything's simplified is 81 pi over 4. Right, so far, we've only been considering cases where axis of revolution was the x-axis. Well, now let's consider an axis of revolution other than the x-axis. So we're going to go ahead and find the volume of the solid obtained by rotating the region between y equals x squared plus 2 and y equals 4 minus x squared about the line y equals -3. This happens to be called the wetting band. So this solid is known as the wetting band. Let's get a picture. So now we want to show x squared plus 2 and y equals 4 minus x squared and y equals -3. Let's bring all that over here. I want to make this as large as possible. So the region is right here. And we're rotating it about this line. Well, why don't we just make this rotate about the x-axis? How do we do that? Well, just move the entire thing up 3 units, right? Or in other words, what we're doing is we're going to move the origin down by 3 units, right? That's essentially what we're doing. We're going to redraw our coordinate system. If we shift everything up 3 units, what we get is 2 new functions, y, x squared plus 2 add 3, and also y equals 4 minus x squared plus 3. Right? Our new horizontal, right? Our new axis is the x-axis, y equals 0. And we didn't adjust these x terms, right? All we have to do now is determine these points of intersection, right? And that will give us our interval. Well, first, let's go ahead and show this new region. Right, so now I can do a region. Region between, we said it was what? Y equals x squared plus 2 plus 3 and y equals 4 minus x squared plus 3. All right, so here's the region. Notice, though, what happened here. Right, they're skipping a lot of the x-axis for clarity's sake. But that's fine. All right, so this is the new image. All right, now we just have to find these 2 points of intersection, and then we have our setup. Well, they're easy to find, right? To find them, just go 5 plus x squared is equal to 7 minus x squared, and solve for x. All right, so this can also be done using Wolfram Alpha. It can also be done on your calculator. Right, for now, I'm just going to stick with Wolfram Alpha. So it's x squared plus 5 is equal to 7 minus x squared. We want to solve that for x. And we get plus or minus 1. So our volume is pi times the integral from -1 to 1 of, now we need to determine our outer. We can determine this by looking at the graph, right? We get 7 minus x squared as our outer. 7 minus x squared squared minus the inner 5 plus x squared squared dx. And at this point, we're out of techniques of integration. So I'm going to go ahead and just evaluate this using Wolfram Alpha. So integrate 7 minus x squared squared minus 5 plus x squared squared with respect to x, right, from -1 to 1. We get 32. Right, I forgot to put a pi in there, so let's go ahead and change that. I'm going to do pi times. Right, and we see we get 32 pi. So this volume is equal to 32 pi. As a final example, let's consider what will happen if we rotate an infinite region. So find the volume of the solid obtained by rotating the region under y equals 1 over x over 1 to infinity about the x-axis. So if we come, look here, let's go ahead and just plot 1 over x. Let's take this one. So I'm going to assume this line right here is 1, right? So it's this region. And remember, this region is infinite, so we'll keep going. Right, if we take a look, right, essentially what's going to happen is we will get a shape that kind of looks like this. Right, and of course this just goes out forever. Kind of looks like a trumpet. So I'm just going to do something like that, right? Because that's going to continue on. Well, the volume would clearly be pi times the integral from 1 to infinity of 1 over x squared dx. Now, this is a p integral. With a equal to 1, p equal to 2. Since this is of the form a to infinity, this converges because p is larger than 1. So we're going to get pi times, it converges, to a to the 1 minus p over p minus 1. Well, this is just 1, right? Let's do that in a different color. So we wind up with a volume of pi. So just some closing comments. The formula we derived for both washer method and disk method, right, is only valid if the axis of rotation is the x-axis. If your axis of rotation is a horizontal axis, other than the x-axis, so it's a line y equals b, well, then our third example here shows you how we can fix that, right? We just adjust it so that our line moves up or down to be the x-axis. If, however, our axis of revolution is a vertical axis, to use the disk or washer method, we will need to write the curves in the form of x equals a function of y, right? And then we could integrate with respect to y. Or we can use the technique that will be covered in the next video, which is the shell method.